Welcome back to the Basic Electronics series. Today we will learning about semiconductor physics and band theory. Here is the agenda: semiconductors, holes and electrons in semiconductors, band theory of semiconductors, conduction band and valence band in semiconductors, types of semiconductors, difference between n-type and p-type, application of semiconductors and numerical problems. So what is semiconductors? So these are the materials which have a conductivity between conductors and insulators. Conductors are nothing but which conducts the electric current easily, but insulators doesn't conduct any current. But semiconductors means it conducts the electric current less than the conductor and greater than the insulator. So here we considering PN junction diode. So why the name is PN junction means this is the N type and this is the P type. So this semiconductor joined N type and P type joined here. So in N region it has extra electrons. Electrons is represented using negative symbol and these come from donor atoms. So here electrons are the main charge carriers. But here this is P region, it has holes. So these are from the acceptor atoms. So here holes are the main charge carriers. It can be represented using positive. So and this is the middle region. So this is the depletion region. So when P and N joined, here electrons move to P side. Here you can see these are the electrons and holes move to N side and these are the holes. So charges cancel near junction. Empty region forms, that is called the depletion region. So no free charges there. So see here we have applied external voltage. If positive to P side, then it is forward bias and current flows easily. But if positive to N side, that is reverse bias and current almost stops. And next is the holes and electrons in semiconductors. So see, this is the silicon crystal and here one vacancy is showing, right? That is nothing but holes. And this moving electrons is nothing but the free electrons. Holes are the positively charged electric charge carrier. But electrons are negatively charged particles. These both are equal in magnitude but opposite in polarity. So these are the two types of charge carriers accountable for the flow of currents in semiconductor. Band theory of the semiconductor. So here also we having insulator and conductor also, and this is the band theory of semiconductor. So it describes how atomic orbitals merge when atoms form a solid, resulting in creation of energy bands and gaps. So see here, this is the insulator. So electron stays in energy levels or bands inside material. So there is two types of band. One is the valence band, one more is conduction band. So valence band electrons normally stay here, but conduction band electrons move here. So electricity flows. So this is the gap between them. It is also called as the band gap. So this is insulator. So here you can see the big band gap. So electrons cannot jump easily. So there is no current will flow. Example of insulator is rubber, glass, plastic. And this is the semiconductor. Here small band gap is present, right? So with little heat or voltage electrons will jump. current sometimes flow. Example of semiconductor is silicon, germanium. But in the case of conductor or metal, there is no band gap. So current flow easily. Example is copper, aluminium. Now, how to remember whether it is insulator, semiconductor or conductor? Remember, in insulator, big gap, band gap. But in semiconductor, small band gap. In conductor, there is no band gap. So, when atoms are closely packed in a solid, their outer electrons interact, splitting their energy levels into hundreds or thousands of closely spaced levels, that is forming the energy bands. So, there are regions where no electron energy level exists. See here, there is no electron energy level exists. So, this is called the band gap. So the space and overlaps between these bands account for the material's ability to conduct electricity. So what is conduction band and valence band in semiconductors? So valence band is nothing but the highest energy band. So that is filled with electrons under normal condition. But conduction band is nothing but the next higher band, where electrons can move freely, allowing electrical conduction. So types of semiconductors. So there is two types. One is intrinsic semiconductor and one more is extrinsic semiconductor. So in extrinsic semiconductor we have two types, P type and N type. So types of semiconductor. First we can see about the intrinsic semiconductor. So an intrinsic semiconductor material is made to be a very pure chemically. This is pure type of semiconductor. Here we having atoms, all are same, right? Silicon atoms. So there is no other atoms here we having, and it is made up of only a single type of element. See, this is also called as silicon crystal. Okay, silicon has 4 valence electron. In this silicon crystal, each silicon atom share its 4 electrons with the neighboring atoms. See here, this is share with 4 neighboring atoms. So we can say that sharing of electrons happens in such a way that each silicon have 8 valence electrons. See here 8 valence electrons. So in this way, by sharing electron, these silicon atoms form covalent band. So these are nothing but the covalent band. This is called the covalent band. In thermal energy, the atom in silicon crystal vibrating. Due to its vibration, that time some of electron may get enough energy. So that they can break the covalent band. Here you can see this electron break the covalent band and move. So here one vacancy is formed, right? So that is called the holes. And these electrons is called free electron. So this is about the intrinsic semiconductor. And next is So germanium and silicon are the most common types of intrinsic semiconductor element because they have 4 valence electrons, and these free electrons and holes contribute to the conduction of electricity in the semiconductor. So electrons are negatively charged particles and holes are the positive charged particles. The thermal energy is capable of ionizing a few atoms in the lattice. So hence their conductivity is less. See here, this is the extrinsic type of semiconductor. So the conductivity of semiconductors can be greatly improved by introducing a small number of suitable replacement atoms. So what it means, to improve the conductivity, we will add small number of suitable replacement atom. So here we added phosphorus and here we added aluminium. So these are called as the impurities. The process of adding impurity atoms to pure semiconductor is called doping. So an extrinsic semiconductor can be further classified as p-type and n-type semiconductor. So let's see about this. So this is the n-type semiconductor and this is the p-type semiconductor. The pure silicon is changed by adding small impurities. So see here, this is n-type semiconductor. Here we added the phosphorus. But phosphorus is pentavalent. So it needs 5 electrons. But silicon needs only 4 to bond. So one extra electron becomes free here. So see, this is the free electron. That's why it is called n-type. So this is the negative. So here electrons are more. So extra electron is present. So current flows mainly by electrons. But in p-type, so here silicon is mixed with the aluminium impurity. So aluminium has only 3 electrons for bonding. So one band is incomplete. See here, this is incomplete and it creates a vacancy. So this empty space is nothing but the hole. So here current flows when electrons fill these holes. So that's why it is p-type, means positive. Here holes are more. So one electron missing creates a hole. So current flows by holes. So this is about the p-type and n-type semiconductor. So here we having one extra electron, right? So it is in the donor. It is donor. So it needs one electron, right? Here silicon needs one electron. So it is the acceptor. So the difference between n-type and p-type, n-type is the donor type and p-type is the acceptor type. So here we having impurity atom is the pentavalent, but here trivalent, means 3. So donor level lies close to the bottom of the conduction band, but acceptor level lies close to the top of the valence band. So here electrons are the majority charge carriers and holes are the minority charge carriers. But here holes are the majority charge carriers and electrons are the minority charge carriers. So but in intrinsic type of semiconductor, that is pure type. So that is tetravalent, means there is 4. So 4 electrons are there. And next is the application of semiconductors. Semiconductors are used in diode, LED, IC, transistor and sensors. So here one mistake is there. This is nothing but LED and this is nothing but the IC, integrated circuit. So these diodes are used for rectification and power supply, and this LED is used in display lights, indicators, bulbs, and we used in ICs in mobiles, computers, TV, calculator, and transistors. Here transistors is used as a switch in electronics, right? It is also used as an amplifier. Then sensors are nothing but many sensors are made using semiconductor materials like silicon, because semiconductors easily react to heat, light, pressure, chemicals. And these are the numerical problems which is most frequently asked in the interview. So in an intrinsic semiconductor, the number of conduction electrons is 7 into 10 to the power 19 meter cube. So find the total number of current carriers in the same semiconductor of size 1 centimeter into 1 centimeter into 1 centimeter. So we know that in intrinsic semiconductor, number of electrons is equals to number of holes, right? Now we having electrons, so that is equals to number of holes, that is nothing but 7 into 10 to the power 19 meter cube. Now we need to find the total number of current carriers. So we know that total number of current carriers is equals to number density into volume. We having volume, that is 1 cm into 1 cm into 1 mm. We need to convert this to meter. Then it will become 1 by 100 is nothing but 10 to the power minus 2. So 10 to the power minus 2 into 10 to the power minus 2 into 10 to the power minus 3. But we don't have the number density, right? Now you need to find the total current carrier density, that is equals to Ne plus NH. So these both are same, right? So add it. So how to add means, here you need to take the common of 10 to the power 19. So then we will get 4 plus 4, that is nothing but 7 plus 7, that is nothing but 14. So 14 into 10 to the power 19 per meter cube. Now we got the value of number density and we having the value which is already given, volume. Then multiply, then you will get the final answer. And pure silicon semiconductor at 500K has equal electrons and holes, that is nothing but 1.5 into 10 to the power 16 meter cube. That this is the number of intrinsic carriers. So doping by indium increases NH, means number of holes we having 4.5 into 10 to the power 22 meter m to the power minus. So calculate the type and electron concentration of the doped semiconductor. So we have a formula Ni to the power square. So Ni square equals to Ne into NH. So intrinsic charge carrier we having, substitute, that is square equals to number of electron we don't have, right? So we need to find electron concentration. So Ne, then whole concentration we having, just substitute. So this is the intrinsic concentration, charge concentration. So now Ne equals to 1.5 into 10 to the power 16 square divided by 4.5 into 10 to the power 22, that is nothing but 5 into 10 to the power 9. But we having whole concentration 4.5 into 10 to the power 22. So compare this, then you, by comparing this you will get to know NH is greater, right? Very greater than Ne. See here 10 to the power 22, here 9. So therefore NH is greater, means majority charge carrier is holes. Here we know, right? Majority charge carriers are holes, that is nothing but p-type semiconductor. So this is the p-type semiconductor. Calculate the type and electron concentration is this one, Ne, 5 into 10 to the power 9 meter m to the power minus 3. So that's all about the semiconductor physics and band theory. For more classes, please watch the upcoming videos. Thank you.